Any sufficiently advanced technology is indistinguishable from magic.
Welcome, everyone, to a very special edition of the Into the Impossible podcast, featuring yours truly, Dr. Brian Keating of the University of California, San Diego, where I am joined today, remotely joined from the Weizmann Institute, all the way in Israel, by a very, very legendary figure in the field of cosmology, and especially in the field of searching for dark matter and potential alternatives to dark matter, and even alternatives to our theory of gravity. And that's Professor Mordehai Moti Milgrom, who is known to many of you, but I will read his introduction at a later date as we go on throughout this conversation. But Mate, Laila Tov, how are you?
It's evening here, yeah. Early in the morning at San Diego, I take it.
Yes. So you might hear some kids getting ready to go to summer camp. So I was introduced to you many decades ago now. I mean, you're very, very famous in the field of cosmology, but most recently by a mutual friend over at Schilling, who was a guest on the podcast. I'll put a link to that somewhere up here or over there, I don't know, in the video, and then on audio, you'll be able to find it, for his new book called The Elephant in the Universe, which is called, subtitle is 100-Year Search for Dark Matter. And he mentions he actually mentions you in the very same paragraph almost as he mentions my late great colleague, Professor Margaret Burbidge, who was the mentor and friend to Vera Rubin. And I want to start first by talking, when Vera Rubin visited UC San Diego, where I am, she worked with Margaret, and Margaret actually taught her how to do rotation curve analysis. So I want to start with a little bit of history. The idea of modified Newtonian dynamics, MOND, what is it? And how did the idea come to you?
So basically, you may know, and the audience may know, that one of the most central questions, puzzles in astronomy, in cosmology today, is what most of the universe is made of. So in very few words, what happens is when you study galaxies and you study the motions of constituents in those galaxies, like the motion of stars and gas, and we use this motion to determine the gravitational pull of the whole galaxy on these constituents, we find that the gravitational pull is much stronger than one calculates just taking the observed mass distribution in those galaxies and calculating the gravitational force using standard dynamics, which is the theory of Newton and also general relativity. In other words, there is a large discrepancy between the gravitational pull that is needed to explain the motions of constituents in galaxies and in systems of galaxies, the discrepancy between this and what the observed matter in those galaxies can supply in the way of gravity. Now, I took another fork at the time. This was the late 1970s, early 80s, and with the proposal that the problem, the discrepancy, does not result from the presence of yet undetected matter, but rather from the fact that we're not using correctly the laws of physics to calculate gravity. So that's an alternative would be, okay, you're using, let's say, Newtonian dynamics, which is a combination of the Newton's law of gravity and the law of inertia. You use this combination of laws to calculate how stars should move in galaxies, and they actually defy this result by moving much faster than you've calculated. So, okay, maybe you are not using the right laws, or maybe these laws are correct, but only have a limited range of validity. But after all, we know that they have been tested, successfully tested in the laboratory in the solar system. So there are large phenomena that are well explained by these laws. But perhaps in galaxies and systems of galaxies and in the universe at large, this is not so. So that is essentially the main idea. Then you asked how it occurred to me. So I ought to mention perhaps that Well, first of all, in my background, I did my PhD in particle physics. That was in the early 70s. And then I switched field to astrophysics. And initially, for several years, I worked in so-called high-energy astrophysics, having to do with explosive or cataclysmic phenomena, such as black holes, neutron stars, X-ray emitting stars, and so on. But towards the late 70s, I decided to switch fields. And I looked around, and this issue of the discrepancy that I mentioned before just began to rear its head in a very meaningful way, partly due to, of course, observation of Rubin and Agu, but also one should mention, alongside with the contribution of Rubin, that also works in the Netherlands using radio telescopes, not the optical telescopes that the Rubin used, but the radio telescopes, who also measured the rotation of the galaxies, and the results of all of them showed quite clearly that this problem exists. So this struck me as an interesting field or problem to start working on when I started, make this decision to switch fields. And I also happened to be about to be going to a sabbatical at the Institute for Advanced Studies in Princeton. And Princeton is the center of galaxy dynamics, you might say. There still are, but there are quite a few world experts on galaxy dynamics. So my decision was just to go and spend this sabbatical year to study the field, prepare myself to embark on this issue. Now, to tell the truth, from the beginning, I had a sort of a guiding idea. So I didn't just go deciding, okay, I'll work on this field, but there was something about those rotation curves that struck me. Apparently, not have the same effect on others, but anyway, to me, it appeared quite interesting. And that was that. Well, let me just explain what the rotation curve is. So, a rotation curve is basically a measurement of the rotation of, you know, that in these galaxies, stars and gas move in more or less circular motion. It's not exact, but more or less circular, and they move in a disk and in a plane. So it's a curve that describes the measurement of the rotational speed of stars, let us say, or gas in a galaxy as a function of the distance from the center of the radius. This would be very analogous to, say, telling us what is the rotational speed of the planets around the sun when you plot them against the distance from the sun, so the radius of the orbit. And certainly as you go further and further outside the galaxies, you expect this rotational velocity to go down this radius. Just as you find in the solar system that the rotational speed of the planets becomes lower and lower as you go to the outer and outer planets. So the rotational speed of Mercury is highest than you go out of Venus, the Earth, Mars, and so on. The rotational speed always decreases. And people expected that to happen in galaxies as well, because you are going further outside from the galaxy. And the fact was that the measured velocity did not go down. They sort of remained flattish. They went up at first, and then they didn't change much as you went out with radius. And the fact that the velocity stayed high and did not go down is the basis for the discrepancy which I mentioned before. So the calculated velocity was going down. The measured velocity was not going down. It stayed up, and just this difference, of course, speaks a discrepancy, which, as I said, is standardly explained with dark matter. But another thing, I remember telling myself, okay, if it's due to dark matter, then dark matter is there. It could be more, it could be less. Its density could, change in different ways in different galaxies. why should there be this apparently universal behavior that the rotation curve stays flat? Okay, it can happen with dark matter, why not? Does not conflict with dark matter, but to me it was a question mark. And then I said to myself, well, maybe it's not dark matter, maybe there is some general law that dictates this, that the rotation curve should stay flat. This is actually, I mentioned my guiding sort of introduction into the field. And when I went to Princeton, in fact, I came across the idea which finally started my working on MOND and so on, only towards my stay there. So for the whole year, indeed, I just studied the field, learning about galaxies, how they behave and so on, but always with a view to finding perhaps some underlying modification of the laws of physics that would give rise to this behavior.
Mm-hmm. And oftentimes when I have a guest on to talk about, say, dark matter, or even specifically talking about Vera Rubin in particular, I get emails from her estate, from Zwicky's relatives. So I get emails from or text messages or comments on my videos saying that Vera Rubin, it was not involved. It really wasn't her discovery. It was all my father, Zwicky. And I wonder, you talk, obviously you've been speaking mostly about rotation curves, but in in the earliest days, of course, Zwicky was, of course, the person who coined the term in German, at least. I think Govert convinced me that it was actually a Dutch physicist, Kaptein, who coined it in English for some reason, and then Oort, etc. But why start with rotation curves? Why not start, as Zwicky did, with the dynamics of clusters, which are also the kind of most massive bound gravitational objects in the universe? Why start with galaxy rotation curves instead of clusters, as Zwicky did?
So the apology for this should not be mine. It was the blame of the whole community. Because what happened in the 30s, Zwicky indeed pointed out, to his satisfaction at least, that again, the galaxies that are the constituents of clusters of galaxies but move with velocities higher than expected. When expected means that what you calculate, this is an elliptical galaxy, but there is also a transparency of a cluster of galaxies somewhere.
Yep.
Okay, but that's an elliptical galaxy. It's not a cluster.
Right.
Of galaxies. But at any rate, so Zwicky pointed out that the velocities of galaxies in clusters are much too high to be explained by the pool of the gravitational pool produced just by the observed matter in those clusters. And then he said, okay, to explain this, he also invoked dark matter. But what happened with this idea between the 30s and let's say mid to late 70s, it just disappeared and nobody talked about it. We can only speculate about the reasons. But I suspect that people just felt that the system were not understood so well so as to actually infer this. So, it happens many times in astrophysics that some measurements are misinterpreted, incorrect, or maybe the idea just appeared to them too bold, unjustified. And anyway, whatever the reason was, it was forgotten. I had never heard about it before. And in addition, I think the rotation curves really brought home the problem to the community in much sharper terms because rotation curves are more accurately measured. So I'll just say one thing, in clusters, okay, what we can measure are just one component of the velocities of galaxies in a cluster. We use Doppler effect to measure velocities, and that gives you only the component of the velocity along the line of sight.
Right.
But to actually determine the gravitational pull, an object, you need its orbit. It's not enough to have its one component of its velocity, and you didn't have that in clusters. Okay, so, but in rotation curves you do, because you know that the motion is circular, and by looking at the ellipticity of the galaxy on the sky, you can tell what its inclination is to the line of sight. So you can translate just this measured one component of the velocity to the full orbit. So in the case of rotation curves, you actually do have the full orbit, and it tells you exactly, or at least to much higher accuracy, what the actual gravitational pull is. So that may have been part of why people may have said, okay, maybe the components of the velocity in other directions. But, no.
Uh-huh.
So it did bring the issue. But maybe also the time was more ripe for this. There were more people interested in galaxy dynamics in the community and so on. So it fell on more receptive ground.
So again, going back to how I came to have you on the podcast today, we go to the book by Govert Schilling, who features you extensively throughout it. And again, this is coming into the work that is really kind of uniquely identified with you, I would say, which is this modification. And what he talks about, he says, I came across the work of Mordehai Milgrom, probably in the 1988 book, Dark Matter by Wallace and Karen. Here was someone with a fresh take on a nagging cosmic mystery. While astronomers were becoming convinced that flat rotation curves of galaxies and the dynamics of clusters could only be explained by assuming that the universe was dominated by dark matter, Milgrom took another approach. He tried to change the laws of physics. Now, here was something heroic. So first of all, besides the fact that you're a Sabra, what gave you the chutzpah to not only take on, changing the laws of physics, but take on Isaac Newton, who's considered by many the father of modern physics, if not all of science. So what gave you that confidence to go, as I always like to ask, what gives you the confidence to go into the impossible, the namesake of this podcast? How did you, come to say, well, actually, it's going to be even more important to go and change the laws of physics?
Yes, well, as to chutzpah, to tell the truth, I didn't think at the time, or at least as far as I remember myself, that it was such a chutzpah. In first, because my background is from particle physics, and people dare to explore less conventional ideas, and astrophysics, let's face it, is a more conservative field, I should say. In a way, I say that people like particle physicists invent the tools, but astrophysicists use them. So they don't like the tools to be taken away from them. So anyway, whatever, seems to me that the community of astrophysicists is more, or at least at the time, had been more conservative. But I didn't at the time actually thought that it took a lot of courage to come up with it. I said, well, why not? I mean, if there's this idea, let's try it. If it works, it works. If it doesn't, it doesn't. We may come back to this issue later. I mean, I was sure that we failed after a short time, but anyway. And, I was even sure that if once I came out with it, people will just jump on the wagon and start working on it. And I was completely wrong, in this so much. But at any rate, I guess that later on, when I already saw what the reaction of people is, it did take more courage than just coming with it. Before I actually knew how people would react. But even then, I don't ever remember myself dismayed or daunted by this rejection. And I should say that from the beginning, I had some very good collaborators. the late Jacob Bekenstein, and it was enough. It's a person doesn't need too many friends. One or two friends are enough for something. And I had him, and he expressed a lot of confidence in the idea, so it was enough for me. And yes, after some time.
Yeah, I want to get to Jacob in a bit, but first, when I think about this story, my younger listeners may not be as familiar, but there was a very famous episode in the history of astronomy where the same person came up with two different approaches to the problem of dark matter, and that was a person, a French mathematician, with a very strange first name, Urbain, and the last name Le Verrie. Yeah, and he first was the one to take observations and make a prediction that Neptune was causing the anomalous behavior of the orbit of Uranus, which was the farthest planet known at the time. Turns out that Galileo actually accidentally discovered Neptune, although he didn't realize it in some observations he made of Jupiter. Just completely serendipitously, Neptune was there in the background, and he thought it was a star. But anyway, besides that, Le Verrier, he hypothesized that there must be some unseen form of another planet. That is a form of dark matter that was previously unseen, that was causing the strange interaction, this tugging on the orbit of Uranus and the planet Uranus. And then then he was proven right. He was actually observationally verified. And then, maybe pushing his luck, he then went out and predicted the explanation of the strange peculiarity of Mercury's orbit, which was another planet that was behaving badly. And he said, this technique worked well for me, so why don't I postulate dark matter is the explanation for Mercury? And he postulated the existence of an unseen planet called Vulcan. And so he was right, and then he was wrong. And I wonder, which do you think was a bigger, was there a mistake or blunder? And then maybe you can explain what Einstein did to correct the error of Le Verrier, and why that was so important.
Well, first of all, it's a very happy analogy with what is happening, of course, with dark matter, because you see motions, unexplained motion of something in a system that is obviously governed by gravity. So in one case, the less daring, shall we say, hypothesis of just some other body in the system that you don't see and contributes to the gravity did work. That was the first example you gave. In the other case, I wouldn't call it a mistake. I think it was the right approach. Not just because it succeeded once, but because it was at the time the more straightforward explanation. So it turned out to not to be the right explanation. But you should judge something as being a mistake or not by how things look at the time it was made. Not very clever. So anyway, indeed, the planet Mercury also showed some very small now anomaly in its behavior. Again, when you calculated the effect of all the known planets and of the Sun, of course, on the motion of Mercury, and it moved in almost the expected way, but not quite. There was a very small anomaly, the region of the energy. And Einstein was working on general relativity, not in order to explain this anomaly, which was not the case in my case. I did suggest the alternative with the prime motivation of explaining away dark matter, but that's not the way he thought about it. Einstein had the theory of special relativity in 1905. Theory of gravity, Newtonian gravity, does not obey the principles of special relativity. For example, special relativity says that there is nothing that can propagate faster than light. And according to the theory of Newton, if you shake an object here, this is felt right away at any distance from that. So, which means that the effect of gravity, of changes in gravity, in the masses that produce gravity, propagate at infinite speed. that does not agree with special relativity. So one motivation for Einstein was to find a generalization of Newtonian gravity that will adhere to the principle of special relativity. And another motivation was to actually generalize it. So special relativity tells you that physics looks the same in systems that move with respect to each other. So that's relativity, but only if they move at a constant speed with respect to each other. That special relativity is essentially about systems moving at a constant speed with respect to each other. Then special relativity tells you how the laws of physics look in those different systems. But Einstein wanted to generalize this to, just general motions. And so.
Mm-hmm.
And it turned out to answer both questions in one fell swoop. And with the introduction of the theory of general relativity, which of course takes its name from the fact that it is generalizing special relativity, but it is also not just this, it is also a relativistic theory of gravity. So it is an extension, a generalization of Newtonian gravity. And it does predict small departures from the calculation of Newtonian gravity, even for planets. Now, its effects are very small in the planetary system, because general relativity kicks in or departs from Newtonian dynamics when you're dealing with velocities that are very high, near the speed of light, or an appreciable fraction of the speed of light. Whereas planets in the solar motion, in the solar system move at, so the Earth moves at about 1 part in 10,000 the speed of light.
Mm-hmm.
So anyway, but it still has a small effect, and it turned out to explain it's the Mercury anomaly without planet. You may have heard that people are now talking about Planet 9. So.
Yes. Yeah, we're searching for it with the Simons Observatory, and the Common Cosmology Telescope is searching for it. We can see it with microwaves because anything above absolute zero, of course, emits that. And then, yeah, we are looking for Planet 9, but it's in the opposite direction. It's not. It's not closer to the sun.
Yeah, but just saying that it was also invoked to explain some anomalies in the motion of other things.
That's right. Yes, and that's frequently what happens in science. In my channel, I talk about the scientific method as not really existing. There is no one scientific method. There's multiple approaches, and sometimes you serendipitously come across anomalies, and sometimes that's quite a fruitful way to proceed. And actually, that dovetails nicely into a question by one of my viewers and friends on Twitter, and that's a professor in the UK, Martin Bauer, who studies particle physics. But Martin asks, there are galaxies for which the rotation curves fit the baryonic matter alone. In other words, galaxies that have no dark matter in them. And so he's asking me to ask you, how do such galaxies that only have ordinary baryonic matter, how do they fit in the context of MOND?
So, first of all, I suppose, MOND predicts that the discrepancy should kick in only at acceleration below. We haven't discussed MOND and what it is and so on yet, because I didn't say what MOND is.
Okay. Well, actually, why don't we start with that then, Mordehai? Because we don't have you have to go, and you've been very generous with your time. It's getting late there. So let's start with what is MOND, and then we'll get into what things are perplexing about MOND in particular, or about non-dark matter candidates such as these galaxies. So first of all, what is MOND, and then I'll show some of the slides that you sent.
Right. So the question is, okay, if I set to try to modify the laws of Newton, let us say, so as to explain the discrepancies without dark matter, you have to take into account the fact that, as I already mentioned, that these laws have been verified and tested successfully in the solar system and in the lab. So you need to ask yourself, I mean, what attribute of the system would tell you that Newtonian gravity is still correct? Okay, or when it is correct, and when you have to replace it with something else. Okay, so in fact, in my initial course, I looked for different system attributes that you could use to differentiate between the solar system, where Newton's laws hold well, and galaxies when they don't. So after a long story, I pinpointed on the accelerations being the crucial property. So accelerations in galaxies are many orders of magnitude smaller than what you encounter in the solar system in the lab. So I sort of hinged this discrepancy on acceleration, introducing a new constant of nature with the dimension of acceleration. This always happens, when we introduce some departure from physics, like quantum physics, it introduced a new constant, the Planck's constant. And in a way, it is a marker. It marks the borderline between the validity domain of the old theory, let's call it the classical old theory, and the new theory. So in relativity, this is plagued by the speed of light. In quantum mechanics, by Planck's constant. In MOND, it is plagued by this acceleration constant, A0. So MOND, in essence, says that as long as accelerations in the system are much larger than this A0, which is the case in the laboratory in solar system, standard physics holds very accurately, Newtonian gravity and general relativity. But when you go to much lower acceleration, there is a departure, and yes, this equation actually summarizes the departure. So I don't know if I should explain it, but it's one way of putting it. You see this mu there. If you just ignore the whole thing with the mu of A over A0, you get F over m equals A, which is just Newton's second law, which is the force divided by mass is the acceleration. MOND introduces this correction, which can be very large. And when the acceleration A becomes much smaller than this A0, which is the constant of MOND, this mu becomes much smaller than 1, which means, which means that you need, F here is the force calculated from Newton.
Right.
So given the force calculated by Newton, when this A is much more than A0, this sort of bold A becomes much larger than you would get from Newton. And that is how the discrepancy is removed, because it says that for the same Newtonian force, actually MOND tells you that the force is that large. Okay, so I'm now ready to try to answer the question you introduced before. I think that what I just said is more or less enough. So, of course, I don't think he means those galaxies, but there are galaxies, or at least regions in galaxies, where the acceleration are still larger than A0. And then you don't expect to see dark matter there. Okay, you don't expect to see a discrepancy. In the language of dark matter, or those who believe in dark matter, you don't expect to see dark matter. But there have been claims in the, okay. So my short answer is I just don't believe this.
Okay.
I can explain to you why in so many words, but
you don't believe that there's no dark matter, or you believe that there's no.
I believe that let's not even say their measurements, but the interpretation of the measurements is just incorrect. And the popular literature tends to accentuate these claims, because the more spectacular they are, the more interesting they are for the readers.
Right.
But there are also other papers that that explain why all this is not really so. Or at least that there are more likely interpretations of the same data that I can tell you just one, for example. Okay, so what they measure, again, as I mentioned before, in clusters of galaxies, are the one component of the velocity. Okay, so only the one along the line of sight, which is measurable by Doppler shift. But in order to estimate the mass of these galaxies, they need the three-dimensional velocity. Now, they don't really know that the velocities in the plane of the sky are larger than what they measure along the line of sight. For example, if this galaxy specifically is rotating, but with such an inclination, it's more or less in the plane of the sky, you wouldn't know it. You will only deduce the mass just based on this one velocity. And in fact, there are claims in the literature that this galaxy is rotating. And that there's no problem. It's a mess of.
Mm-hmm.
But the basic answer is I just don't.
I see.
And many others, I should say, and there are papers about it. I mean, so actually, there are much more mundane explanations.
Right.
In any case, it's a problem for dark matter, but never mind. That's not mine.
Okay. And then there's a question that's occurred many times in the literature, and then in my audience, Tim Johnson, who's a friend of the show, listens to the show. He's asking, can you share your view on why the bullet cluster is a challenge for MOND, and how can it be explained by MOND? So first of all, what is the bullet cluster? I'll show a picture of it on the screen.
So the bullet cluster so let's start. So the bullet cluster is a cluster, or actually a pair of clusters that have undergone a collision. We see them just a few hundred, I think, million years after the centers went through each other. Okay, we see them on the sky. What you see here is, I think, the X-ray picture.
Okay.
These two clusters contain gas, hot gas. This gas radiates more or less in Röntgen, in X-rays.
Mm-hmm.
And you can see that. And this map basically tells you where much of the baryons are. The baryons are the standard matter. So in clusters, it is known to be dominated by the hot gas. So essentially, they tell you where the baryons are. Now, what you can also study this double cluster with so-called weak gravitational lensing by using the distortion of the images of galaxies that are far behind in the background behind this cluster. Right. So these are the two sort of bluish things. So the reddish things are what we just saw before. The X-ray emission from the hot gas, and this is where the hot gas is. The bluish things are where the galaxies in the clusters are. So the cluster just went to each other. Imagine yourself that the two clusters before they collided contain this gas and galaxies mixed together. But once they collided, because the gas cloud essentially cannot very easily go through each other because they're sticky, so they stayed more or less near the center. But the clumps of galaxies in the cluster just went through, and you see them as these two. Okay, so however, from studies of distortion of images of galaxies behind the scene, we can tell where the dark matter is. Okay, we can tell, we can map essentially the total matter in the system. And it turns out to be where the galaxies are.
Mm-hmm.
Okay, so more where the bluish things are. So the claim is the following. No, you say that, according to MOND, the claim. According to MOND, you should find sort of the discrepancy, or you should find this phantom or putative dark matter where the baryons are. Yes. So, but in this system, they seem to be not where most of the baryons are, which is the reddish things, but where the bluish things are. Okay. So that was banded as a proof of the existence of dark matter. So. Well, the answer, or our MOND answer, tries to answer is several. So first of all, the problem was not new. That we already knew from the 90s that MOND does not explain away completely the mass discrepancy in clusters of galaxies. Okay, this is still a standing issue with MOND, but even much before the bullet clusters and in analysis later, before, whatever, there are several analyses that show that if you apply MOND to clusters, So in individual clusters, not ones that underwent collision. There's also a discrepancy. It's let's say a discrepancy of a factor of 10, let us say. So the visible matter is just a tenth of what's needed to supply the gravity.
Right.
So you need like 9 times more dark matter than you have visible matter. If you apply MOND to this system, it reduces the discrepancy greatly, but it still leaves a discrepancy of a factor of 2 roughly. So you would still need in these clusters, not speaking about the bullet now, but just about isolated tens of clusters, you would still need some component that we haven't discovered yet. So some people prefer to say that this is maybe sterile neutrinos that can fall into clusters but not into galaxies, because the famous argument that they are too light to fall into galaxies. But my own explanation is that yes, clusters still contain some baryonic matter that we haven't detected yet. It's not an issue at all, because you only need as much as you already see. And it could be in a component that hasn't been discovered yet. Could be that starts from cell population. Could be called gas clouds. There are quite a few papers on this. And you may know that there is also something called the missing baryons problem.
Yeah.
We think we know what the total number of baryons in the universe is. We know this from nucleosynthesis, formation of the light elements, and so on. So we think 4% of the closure density of the universe is baryons. But where are they? I mean, a tally of baryons as we know them today can account for roughly 50% of the baryons. Okay, so where are the other 50%? And all that you need to explain away the problems among clusters is just about 5%. If you sum over all clusters and all that you need in clusters, you need about 5% of the baryons that now exist. So it's a small fraction of the baryon budgeted universe. So it could easily be. I'm not saying that I know that this is the answer, but it could be a mundane answer. We would very much like to know. It is still an issue. I consider it an issue, an open question in one, but one that at least can have a simple explanation. And I should say that, okay, if you now know, if you take what you learned for single clusters, for isolated cluster, then the bullet cluster just behaves in the way that you expect. Because this extra component has to be non-dissipative for other reasons, and so when the two classes go together, collide, this extra component should follow the galaxy, not the gas. But anyway, that's the explanation.
So, looking at other challenges to MOND, there are questions about other types of dark matter. You just brought up one type, sterile neutrinos or axions. But I often point out there's a detection of dark matter, at least that's been claimed for over 22 years, and that's by the DAMA experiment. And I wonder, can you give me your perspective on DAMA? Is it a challenge? And just more generally speaking, if the liquid and noble gas detectors like Xenon 1-ton, which is co-run here at UC San Diego by my friend and colleague and past guest Kai-Xuan Ni and friend and past guest Alina April, are there challenges to MOND if DAMA is to be taken seriously?
Well, let's start by saying that certainly if dark matter is detected, then it is a challenge. It's not just a challenge. It's just take the carpet from underneath. But if there's dark matter, then there's no need for it. But this
Sorry, Moti, it's a little hard to hear you. What did you?
I'm saying that if dark matter is actually discovered, then certainly it's a challenge.
If particulate dark matter is detected, right?
Yeah, but DAMA, I mean, you don't have to ask me, ask anyone else, even those who believe in dark matter. I don't think they actually believe in DAMA. Well, as you may know, it conflicts, by many orders of magnitude with other experiments that don't find it. There are also as far as I know, similar experiments using the same type of detectors that claim that they haven't seen anything. And there are mundane explanations, but look, I'm not the right person to ask.
Right.
I have absolutely no idea of what could go wrong with DAMA, and I don't have a way of.
Yeah. But generally speaking, right, if there was in other words, is there no possibility that both flowers could bloom, both the dark matter in particulate form and a modification, or is it really one or the other?
Well, in principle, it can be, and as you know, I watched bits of your interview with Sabine Ostenfelder, which at least at some point has advocated or endorsed this hybrid idea of superfluid dark matter.
Mm-hmm.
I should say it's not the first, it's the most famous one, because the people involved are more vocal or larger audience. But similar ideas have been suggested before. For example, by Luc Blanchet from Paris, who suggested that the universe is just filled with a gravitationally polarized medium,
Mm-hmm.
such that on large scales it works as dark matter, and on small scales it reproduces MOND. And superfluid dark matter is conceptually at least a similar idea, is that those galaxies and the universe at large is again filled with a fluid that could be either in
Mm-hmm.
standard phase, in which case it works as dark matter in the sense that it acts by its gravitational weight, gravitational pull, but that in galaxies it can form a superfluid phase, and there it doesn't act mainly by its gravitational pull, but rather it modifies the interaction between baryons, between stars and so on, so as to reproduce the effects of MOND. Now, these are hybrid models. That I can't say that it cannot be, but I don't like them very much for several reasons. Because on aesthetic ground, it's like the easiest way out. You see, you stick together two different things. If you already have one sort of outrageous idea, you want. And you see it succeed in a large range of phenomena. Why not try to improve it so it succeeds also?
Right.
When you put two such things together, they tend to fail in the region where you stick them, right? Because this one works here, the other one works there. What happened? And this is a common thing that occurs. There is, I don't know, it's not very famous at the time where there was a struggle, let's say, between the Ptolemean geocentric picture,
Mm-hmm.
Everything goes around the Earth, including the Sun, and the Copernican system, where everything goes, not everything, but at least the planets go around the Sun. And then there seem to be advantages to the two things. And so Tycho Brahe put a hybrid, suggested the hybrid. Did you know about this? So I know it's very famous, but he said, let's have all the planets, go around the Sun, except the Earth.
Yeah.
But the Sun, with all its this entourage of planets, go around the Earth.
Yes.
So it has the benefits of the Copernican system, but at least as far as parallaxes were not yet observed. So, parallaxes were the clinching argument for the Copernican system, that we actually, by the motion, this apparent motion of things on the sky, we know that it is the Earth that goes around the Sun. But anyway, before that, it actually combined the benefits of Copernican system with those of the Sun. You could still be okay with the Bible, right? The Sun goes around the Earth, so it could stop at Gibeon, and as the Bible dictated, and it was okay for others. So it was a hybrid. But we know what happened there. So on the aesthetic ground, I don't like the hybrids. Historically, they haven't proven to work. and it seems that even the superfluid idea isn't really doing very well. I mean, even Sabine had recently a quote of the paper where they claim that it doesn't quite work for rotation curves. So, anyway.
Right. Well, Moti, I know it's getting late there, and you've been so gracious with your time and the audience questions, answering all the audience questions. I want to ask you one last question, which is pertinent to the name of the podcast, which comes from one of Sir Arthur C. Clarke's famous laws. He actually had 4 of them, and they're controversial. What's the naming? What's the counting of them? But I want to ask you the one that's pertinent to the name of my podcast, which states the following: the only way of determining the limits of the possible is to venture beyond them into the impossible. So that's where the name of the podcast comes from. And I want to ask you, in the context that I ask all my guests who are so gracious like you are, I want to ask you, what gave you the courage as a 20-year-old or 30-year-old, if you can go back to your former self and give some advice, some life advice, what would you say to give the courage to go, as you've done, the chutzpah, into the impossible?
Yes, well, because this theme of possible, impossible actually accompanies me along the way, because so many times I've heard this is impossible, this is impossible with MOND. I mean, so at first they said, okay, fine, MOND works for galaxies, but it will be impossible to explain light bending and gravitational lensing. So it took 20 years, but there was finally the relativistic theory that did get lensing correctly. And then people say, well, but you can't get the CMB. It's impossible to get the CMB correctly with MOND. And just last year, there was a paper by Skordis and Zloznik suggesting a relativistic MOND theory that does reproduce the CMB fluctuation. So from the very beginning, for me, this possible, impossible, like the following one, that, when I started thinking about it, I didn't think it would be impossible, but I was sure that the probability is very low that I will actually be able to modify the laws of physics. Of course, I'm like everyone else, not crazy. So I had this initial idea. I said to myself, well, I'm sure in a day or two I just show that it is wrong. It's impossible. I mean, it's highly unlikely, at least that's not possible. And then I work because it impinges on so many phenomena. I'm sure I'll find something wrong. It didn't happen after a few days. I worked it out again and again. I invested more time and so on. And every time, things that initially looked impossible, or at least highly improbable, turn out to be possible. And if it's any, of course, it doesn't. This way of argumentation doesn't work. So in the individual, I don't know how good an idea is to just tell entirely the impossible, because chances are, in any case, if it looks impossible, it's probably at least improbable, so you may be wasting your time. Mm-hmm. But as a community, certainly, I mean, some of us should try what looks like impossible. Otherwise, we're not going to get beyond the boundary of already, right? So for individual, so what is good as a general advice for the community? The community should always send, or at least should accept such people, with open minds. At least not give trouble when they're trying to do something like this, because it's very important for the community to explore beyond, what appears impossible.
Absolutely. Very good. Well, Moti, toda rabah. I want to wish you Laila Tov. Thank you for coming on. Yes. Thank you very much. Yes.
Any sufficiently advanced technology is indistinguishable from magic.